Look at these two identical desks. If one person measures the top using their handspan, they might count exactly 6 hands across. But if someone else with smaller hands measures the exact same surface, they get 8. Imagine sending that measurement to a carpenter. If you ask for a desk that is 6 handspans wide, but the carpenter builds it using their own hands, the furniture you receive will not fit your space. Relying on our own bodies to judge size guarantees this kind of confusion. To accurately communicate physical dimensions, we need a standard that stays exactly the same no matter who is doing the measuring. In 1960, scientists globally adopted the International System of Units, or SI units. This is an agreed-upon system of measurements that ensures a length recorded in Tokyo means the exact same thing in Toronto. Every proper measurement you take with this system requires 2 parts. There is the magnitude, which is the number telling you the amount. And there is the unit, which is the specific standard you are comparing that amount against. For length, the base SI unit is the meter. To picture it, a standard interior doorway is usually just about 1 meter wide. You can take that exact same unit and stack it to measure enormous structures. The Burj Khalifa in Dubai, pictured here, reaches a magnitude of 828, all measured in those same standard meters. If you just say a building is 828, that number has no real-world meaning. By attaching a unit, you lock that number to a physical reality everyone can understand. Having a perfectly defined meter is useless if you measure it incorrectly. The tools we use every day, like a common ruler, require specific physical technique to yield true results. This diagram illustrates what scientists call parallax error. This is the apparent shift in an object's position when you view it from an angle. If your eye isn't directly above the measurement mark, the alignment distorts and you will record the wrong number. If the 0 mark on a wooden ruler is worn away, align the object's edge exactly with the 1 centimeter mark instead. Read the number at the far end and subtract your starting point to find the true length. A standardized unit gives you the vocabulary of measurement, but it is the physical discipline of the observer that actually secures the correct answer. That discipline gets tested when the object you are studying isn't flat. You cannot wrap a rigid wooden ruler around the thick, irregular trunk of a tree to find its circumference. To capture that dimension, you can use the thread method. By wrapping a flexible piece of string tightly around the curve and marking exactly where it overlaps, you capture the true distance. You then pull that string straight against a flat meter scale to read the length. That same logic applies to massive winding distances. This image shows the Great Wall of China navigating severe mountain ridges. Stretching over 21,000 kilometers, its total length has to account for every single rise, fall, and curve along the terrain. By adapting our technique, we can take the complex, chaotic curves of the physical world and translate them into straight, readable data. Capturing the length of a static object is one challenge, but the process of measurement changes completely the moment an object starts moving through space. Consider the view from inside a moving bus. If you measure your position against the seat beneath you, you are entirely stationary. But if you measure your position against the sidewalk blurring past the window, you are traveling at 50 kilometers an hour. To determine if something has actually moved, you first have to establish a reference point. A reference point is a specific, fixed location used to compare the changing positions of other objects. Because motion is a change in position over time, it is entirely relative. Unless you lock in a specific reference point, your eyes will struggle to tell you what is actually moving and what is standing still. Once a fixed reference point is set, you can accurately track how an object travels. The simplest path is linear motion, where an object moves continuously along a single straight line. In this diagram, we see circular motion. The Earth is constantly moving, but its path traces a continuous curve around a fixed central reference point, the Sun. You also see motion anchored to a fixed point in objects like this grandfather clock. The pendulum exhibits oscillatory motion, swinging back and forth through a central resting position. While the swing itself is oscillatory, the pendulum also demonstrates periodic motion. Oscillatory describes the physical path it takes through the air, while periodic means that the movement repeats itself at strict, highly predictable intervals of time. From tracking the width of a table to mapping the orbit of a planet, observation alone is rarely enough. By securing fixed reference points and applying standard units, we bypass the illusions of our senses and accurately document the physical world.